Okay, we're in Chapter 8 still, and we are in Part 2 of 8.3. We are talking about another one of the tests to discover ways to, find out if a series is convergent or divergent, not especially finding out whether the series converges to a particular value. So in this section, a p-series test, we want to use properties of p-series and the harmonic series. And we have a definition of a p-series. A p-series is a type of series that follows the following pattern, where p is a positive constant. For p is equal to 1, the series, the summation from 1 to infinity of 1 over n is 1 over 1 plus 1 over 2 plus 1 over 3 is called the harmonic series. If you recall, when we were working with integrals, talk about the integral test, the integral of 1 over x dx, it was divergent. So we'll kind of bring those into play with respect to many of our p-series, because you remember, if they converge by the integral test, if that works, we can often use that. But here we go. Convergence of a p-series. If you see a series and you have this summation from 1 to infinity of 1 over n to the p power, then 1 over 1 to the p, 1 over 2 to the p, 1 over 3 to the p, all added together, then the proof really follows from the integral test, but it converges if p is greater than 1. It diverges if p is between 0 and 1. So an informally proving this, that the harmonic series diverges, we could take and we could group all of the terms, and we could start with 1, well, that's equal to 1, and then we could add 1/2 plus 1/3 plus 1/4, and that would be greater than 1, a number greater than 1. And then we could go from 1/5 to 1/12, that would be a number greater than 1. And we could continue to do this ad infinitum. And you can see that if they were all greater than 1, we could keep on doing this, and we would eventually see that the series diverges. Okay, so that's it for that. So then convergent and divergent p-series, it's really as easy as this. We would just say, okay, well, we look at the form where we have the summation of 1 over n to the p, and we would just say, all right, well, we can see that p is equal to 2 here, which is greater than 1. So we can simply say that by the p-series test, the series converges. And then for the next one, we look at that. And you know that you might want to do a rewrite, but you guys know that the square root of n is n to the 1/2 power. So p in that case is equal to 1/2. So we know since p is equal to 1/2, then it's less than or equal to 1. So we know that the series diverges. And again, we have the condition met. P is between 0 and 1, so it diverges. In the last one, where p is equal to 1, we have the harmonic series, and we know that if p is in this range where it's from 0 to 1, but it could be equal to 1, then we know that the series also diverges, and it is the divergent harmonic series. We'll talk a little bit more about the harmonic series in school. All right, and then I just wanted to compare these because sometimes students can get these a little bit confused. We have the convergence of geometric series that's of this form, where we have the summation, or the series from 0 to infinity of a r to the nth power. And the series converges when r is less than 1, and the series diverges when the absolute value of r is greater than or equal to 1. So correct me on the absolute value of r is less than 1, the series converges, where the series diverges when the absolute value of r is greater than or equal to 1. So keeping that clear, because it kind of sounds a little bit familiar, and you're dealing with powers and exponentials, so you kind of have to keep your mind on this, where in this case, in the first case, you're talking about r being the base, right? You have 1/2 to the nth power. In the series, the convergence of p-series, you're talking about p being the exponent to the base of n, where the n in the geometric series is the exponent, n is now the base for the p-series. So recall that we worked with these a lot with integrals, and when we were doing integrals, the integral of 1 over x squared converged, the integral of 1 over x diverged, and we dealt with that. It is the same type of rule, and we often do that. So you have your convergence of p-series and geometric series. I just wanted to review those. They are something that students will often mistake. So we will be working on integrals as well to prove these, but that's it. Very short. And just to complete this lesson, 8.3, part 2 on the P-series tests. And like I said, tomorrow we'll introduce a couple more for you. So have a good night, and I'll see you when I see you. This is Allenator out.